everyone, I'm Zhang from Personal Robotics Lab, Imperial College London. Thank you for joining this presentation. Today I'm going to talk about my work, learning grasping points for garment manipulation in robot-assisted dressing. Many recent studies on robot-assisted dressing, including our previous work, usually simplify the setup of the initial robot configuration by manually attaching the garments on the robot end-effector and positioning them close to the user's arm. To relax the constraints on the initial configuration and further expand its applicability, a fundamental challenge is learning suitable grasping points on garments that facilitate robotic manipulation. In this paper, we address this problem by introducing a supervised deep neural network to locate a predefined grasping point on the garment. To reduce the amount of real data required, which is costly to collect, we leverage the power of simulation to produce large amounts of label data. The network is jointly trained with a large amount of synthetic datasets of depth images and a limited amount of real data. We also introduce a robot-assisted dressing system, which takes grasping orientation computation and robot garment collision avoidance into account. As shown in this figure, a gown is naturally hung on a rail to imitate home or hospital environments. Here, we use the convolutional neural network to estimate the Cartesian positions of a predefined grasping point on the garment. Depth images are used as the input modality for their invariance to different colors and textures. The output of the network is the Cartesian positions of the grasping point. Having the predicted grasping point positions, we present a grasping strategy for actual robot execution. We calculate the orientation for each grasping point from the garment point cloud. Then the robot approaches the garment for grasping. The trajectory of the robot approaching the garment is planned to avoid collisions between the robot and the garment, which may lead to changing the grasping point positions before the actual grasping is executed. Then the robot autonomously grasps the hospital gown hung on the rail, brings it close to the user, and successfully dresses the upper body. Here, the user's posture is recognized in real time using the HRNet from Microsoft. As we all know, real-world label data, especially in the domain of robotics, is notoriously costly to collect. To reduce the amount of real data required, the power of simulation is usually leveraged to continuously generate large amounts of label data. However, training models with synthetic depth images may not readily transfer to real-world applications, and thus the prediction accuracy cannot be guaranteed. So we decided to train the deep neural network with both synthetic and real datasets. The idea is to use as little real-world data as possible with the help of simulation to generate accurate grasping points estimation. The left video here shows how we collect the real garment data. A hospital gown is naturally hung on a rail, while the hanging point is randomly around the collar of the gown. A Kinect camera is placed in front of the garment. We predefine a grasping point and put a black marker on it. We continuously hang and remove the gown from the rail and obtain a real garment dataset consisting of 6,000 depth images, as well as the grasping point positions recorded. The right video shows how we collect synthetic data using the physics simulator Autodesk Maya. A 3D model of the real gown has been built. 36 cameras has been put around the garment to capture depth images from all points of the view after the garment falls and stabilizes based on the simulated gravity. This simulation environment is manually adjusted to roughly match the appearance and dynamics of the lab setup, including camera positions and parameters. This process is autonomously repeated, and 62,000 simulated images has been saved. Having the predicted grasping point positions, we design a grasping strategy for robots. We compute the specific orientation for each grasping point from garment point cloud. The left figure here shows the ideal grasping orientation for robot end effectors. Y-axis should be aligned with the gripper opening and closing direction. We define the surface normal as point p hat as y-axis. The surface normal is estimated from point cloud using Open3D library. Z-axis should be aligned with the parallel fingered direction, which is obtained by computing the cross product of vector HP hat and the surface normal. Accordingly, we obtain x-axis, which should be approximately aligned with the garment edge direction. Garment point cloud from the Kinect sensor is integrated in MoveIt using Octomap, which prevents the robot garment collisions during the process of robot's gripper approaching the garment. To validate the proposed methods, we conduct 2 experiments and benchmark our results versus 4 baselines, including network training with only synthetic datasets, network training with only synthetic datasets modified by adding simulated depth noise, network training with only real datasets, and network training with simulated datasets modified by an image-to-image translation approach. Each baseline here corresponds to a method used in one of the literatures. In the first experiment, we investigate the accuracy of our proposed grasping point prediction method. We trained network with all synthetic images together with different amounts of real images respectively. In the figure here, the x-axis presents different amounts of real images. We can see that jointly trained network using synthetic data with a limited amount of real data can significantly improve their prediction accuracy against training with only synthetic data. Similarly, it can also improve the prediction accuracy than training with only corresponding amount of real data. We can also see that synthetic data significantly improves prediction performance when very small amounts of real data is available. When we use cyclogram to synthesize realistically looking sim-to-real images, we have only observed a very weak difference here. In the second experiment, we deployed the trained network on the physical robot to evaluate grasping and addressing performance. For each training model, 50 replications of trials have been carried out. Here we can see when jointly training the network using synthetic images with 100 and 500 real data, the grasping success rates rapidly increases respectively against simulation-only training. Another interesting observation is that network training using synthetic data with another 500 real images attains around 78% of grasping success rate, which is a comparable performance to network training using 1,000 real images only, resulting in a reduction of real-world data by 50%. Here we show some video examples of our results. In this page, these 3 videos show that the training network using only synthetic data and only real data can lead to inaccurate grasping point prediction, which causes upper body dressing failures. However, when we train the network using synthetic data and real data together, the accurate grasping point estimations lead to successful garment grasping and dressing. Here we show when we do not consider the grasping orientation computation and garment robot collision avoidance, the grasping and dressing may fail. We also have some failure cases. The garment can tangle itself during the process of the robot approaching the user. And also the robot can grasp multi-layer of the garment. And these cases make the sleeve opening not easily accessible to the user. In conclusions, we propose a supervised deep neural network which yield accurate grasping points estimations using a limited amount of real data with a large amount of simulated data. We also consider the grasping point orientation and the robot garment collision avoidance. For the future work, we would like to tackle the failure cases when the predicted grasping point is occluded. Thank you so much for your listening.